My first question is uh, on the 3D imaging sensor only. So, what it is about and how it is different from the traditional thermal sensors in the market.
Certainly. So thanks for agreeing to have a conversation today. My name is Wade Appelman, and I'm the Chief Business Officer for Owl Autonomous Imaging. Let me just briefly, and I'll get to your question very, very quickly, but I think it's important to have some context as to who we are and what we do. Uh, Owl is a thermal and computer vision company. We have a solution that includes a thermal focal plane array, which is an image sensor that detects objects that radiate heat or radiated energy. And I'll explain how that works in a second. And then we also have computer vision algorithms, which are uniquely designed for thermal. And we'll talk about how that is used in the automotive industry specifically, which is our first target markets for pedestrian identification at night to make it a safer place for pedestrians and vehicles to coexist. The company is headquartered in Rochester, New York, which is a very famous location in the United States for imaging. It was the home of Kodak, and it has incredible history, and that's how we were able to really get together our team of experts in this area. And so, what I'd like to do now is maybe dive into a little bit of your question is what is thermal imaging and what are the problems that are being faced here. This is something that is actually being talked about in the big picture all over the world. These are headlines that came out as recently as this past week, actually. The New York Times ran a story on Monday, December 11th, that talked about why are so many pedestrians dying at night. And this graph is exceptionally telling. It goes back to the 1980s, and you can see a nice decline in pedestrian fatalities when it's during the day. But around 2010, we see pedestrian deaths going up dramatically, almost 77% increase over that 10-year period. Forbes magazine has covered this as well, of how thermal imaging may help bring a solution to help this really horrible trend. And Vox talks about how U.S. pedestrian deaths at a 40-year high. If I go back and bring in a worldwide perspective, there's almost 700,000 pedestrian fatalities each year, and of those, 76 are occurring at night. And we're seeing regulations around the world, so not just the United States, but in the EU and Asia-Pac countries as well, where they're going to be mandating to automobiles and automobile manufacturers that they're going to have systems in place to detect pedestrians at night. And we're seeing a lot of research being done such that what's happening now is that test houses are taking production vehicles and running them through the scenarios that they know the mandates are going to enforce. So one of those scenarios that have to happen is, can a car safely brake at night when there's a pedestrian walking across a dark street with oncoming headlights? So just think about your own experience with that. When you're driving a vehicle, your eyes are blinded if there's an oncoming headlight and a pedestrian is in the shadow outside of the cone of your headlights. When that test is done with today's production vehicles, only 1 out of 23 production vehicles, 2021 production vehicles, passed this test. And that they had to have high beams on, and there's even some questions as to how fast the vehicle was going at that time. And that's because the current sensor suite that are in vehicles today simply don't work. So I'm going to pause here for a second and see if you have any other questions. I know you asked a big, broad question, how does thermal work? But I think it's important to understand where it fits and why it matters. So the way a sensor suite works in vehicles today is the way it works is these sensors, and they could include all different types of sensors, and I'll talk about those sensors in a second. The sensors detect is something there? So it just wants to know, is there something in front of the vehicle, whether it's driving down a dark alley or down a highway? You need to know, is there something there? And there are sensors that will do that. But the next thing you need to do is you need to know, what is it? You need to classify is it in order to make a decision. Is it a person in front of me? Is it a box in front of me? Is it a car? Is it a deer? What is it? Because I'm going to make a different decision as to how to react depending on what's happening. So you need to classify something. The next thing you need to do is you need to do ranging. You need to know how far something is. What's the distance that that object is? So you can make a calculation like you do when you drive. Oh, that's far away. I can slowly move around it, or I better jam on the brakes no matter what. So the last thing is acting. So you need to detect, classify, range, or act. And that's what vehicles do today with the sensors. So now we'll go a little bit more technical and a little deeper here. And we'll talk about the sensors that are used in today's automobiles to make those decisions. So what cars have today, almost every car today that has an ADAS system, automatic emergency braking systems, or automotive driver assist systems is what that acronym stands for. They have cameras, regular visible light cameras, also referred to as RGB cameras, red, green, blue cameras. They detect color. Those cameras can be used to detect if there's something in the road. It's used for that classification function. And in certain cases, it's even used for ranging. The problem with the camera is, just think about a cell phone camera you have or your own lives. If it's dark, it doesn't see. It's the physics. It's just the way it works. There's nothing you can do about it. If there's no light, a regular camera just doesn't see. So what they do too is they add radar. Radar works on wave pulses, but radar is very, very, very simple and doesn't really work to do object classification. It just doesn't have enough depth of information. It's a blob. It says, yeah, there's something there, but we don't know what it is. But it can be used for accurately ranging when used in conjunction with the camera. Radar works at night, but it can't see and classify. So people have talked about bringing out lidar. And lidar does pulses of light that reflect back to the detector, and it can create what's called a point cloud. These are very dense point clouds, and they kind of look like a RGB camera image with pixels, but there's not nearly as many pixels as there are in a camera. So the images aren't great, and you can't use them for classification. It's really good to tell you if something's there, and it kind of tells you what's happening from a mapping perspective, but it's really expensive. It's not widely deployed yet. It has some promise, but it will never be used for classification. So there's another kind of camera that's out there, and that's called a thermal camera. And a thermal camera works very, very differently at the physics level than an RGB or a visible light camera. A thermal camera can see in complete darkness or blinding light. And I'll show you some examples of that in a few minutes. But it works on electromagnetic energy. It's truly passive. Every object in the world gives out radiated energy in the form of a heat, okay? So your body temperature in Fahrenheit is 98.6 degrees. A surface has a temperature, and there's micro differences in that temperature. So if you have of these different objects, a temperature of different objects. So if you have a very sensitive sensor that can detect those very minute degrees of temperature variance, it can create an image based on that temperature signature very, very, very easily. Okay, and we operate in the infrared spectrum in a very particular wavelength. So light objects work in the infrared or the near infrared space, which is where lidar works, and thermal works in the long wave infrared spectrum. So again, getting a little technical here, we operate at the 8,000 nanometer to 14,000 nanometer wavelength, whereas lidar runs at about 905 nanometers to 1550 nanometers, and visible light is in about that 400 to 600 nanometer range. So that physics will dictate what it can see through. Can it see through fog, rain, snow, dust, and smoke? Will it be occluded? Will it allow for partial occlusions? And one of the technologies see in color. So cameras see in color, thermal sees in grayscale, right? But there's a lot of questions about, where does thermal work? There's been a lot of thoughts over the years or misperceptions as to, does thermal work in the snow? Does it work in driving rain? Does it work on a hot day? And the answer is yes. As you can see from these videos that I'm showing here, these are thermal images running in those different environments. In the lower left-hand corner of the image, you'll see a test in fog, and it takes 4 different wavelengths from that visible light spectrum, that 400 nanometer to 800 nanometer on the far right-hand side, as you see here, and it also compares how well through thick fog does far infrared or long wave infrared, the technology that we're talking about here at OWL. And you can see that we can see the target, but you can't see it in visible light. And the last thing I'll share with you is this picture in the upper left-hand corner. This was a photo booth that we did in an event in the United States at Consumer Electronics Show last year, where we took a picture of people with the lights on with the standard RGB image. So there's Mark, there's me, there's somebody else from our company in the middle. You can see very clearly how it looks. And that's what it looks like in thermal. Okay, you can see, you can't see color, but you can see very clearly they're humans and you understand what they are. Then you turn the lights off. And when you turn the lights off, the RGB camera just doesn't see anything, but guess what? Thermal looks exactly the way it always has. So that is the essence of how thermal works and how it works and looks in all of the different environments. And I'll drop into how the technology works in a second at our product level, but I wanted to make sure that this answered your questions about how does thermal work and how does it compare to other sensing modalities. Any questions at this point?
Uh, what is the uniqueness of your product, your 3D thermal imaging sensor?
Right. So what the challenge that has been out in the market is thermal imaging has been around for a while. Okay, it's been used in military use cases. It has been used in high-end production vehicles, but the reason it has not been widely adopted in the use cases for automatic braking or even really autonomous driving, robo-taxis, long-haul trucking that are out there, is the cost of thermal imagers today are measured in the $1,000 to $10,000 range for a single camera. And that will never be brought into an automotive application with the costs being that high. The other problem has been the resolution, the number of pixels. You need a lot of pixels to identify an object that's far away and know, is it a person, is it a place, is it an animal? So resolution matters. So what we have done, simply put, at OWL, is we fix the cost and resolution problem. We have a solution which is a fully digital design of a thermal camera, and we have brought that down significantly, such that the industry will be able to get thermal cameras in the hundreds of dollar range, depending on the size and resolution. And we're going from what's called quarter VGA, which is the industry standard, or VGA, which is 400 by 700 pixels maximum. We're figured out a way to get high definition, or HD, millions of pixels, so 1200 by 800 pixels, into a low-cost device. Combine that with our computer vision software, the AI software, that is really what makes OWL unique, is the ability to hit the cost target, the resolution, plus the computer vision software. Does that make sense?
Yes. So how quickly can your technology find out what an object is and how far it is?
Sure. So that's a complex question to determine how quickly and how far, because it really is dependent on a number of variables. But I'll try to give you a standard answer. We're a camera, so we can work as fast as a regular camera works. We operate at up to 60 frames per second, okay? And a typical use case for being able to identify something is much slower than that. So we're almost instantaneous to be able to tell the computer there's something there. And then the next question is, how far can you see? It depends on the lens. We can put a telephoto lens on the product, and we can see miles and miles. We shouldn't say some miles and miles. Let me again, a picture's worth a thousand words here. This image right here, you can see here. This is a video that's taken in a driving rainstorm. But that car that you see where my cursor is 1.5 kilometers away from the camera. So you can see very, very far if you put a telephoto lens on it. But typically you need to be able to see about 90 meters in a wide field of view in order to do object classification and safely stop when the vehicle's going at about 40 miles an hour.
Okay.
And that's no
So,
problem.
okay, so you talked about that AI, with the help of AI, you are, making this possible. So how AI and CNN is helping doing this? What
Sure.
softwares you use?
Sure. So the simple way to let's address how our software works and what it does. So I think the best place to start is with the picture that looks like this. So what our solution is for OWL is we have a camera, the thermal camera that I've just described, and we have our convolutional neural network software algorithms, which runs on an NVIDIA processor. It can run on other processors, but today our proof of concept software system runs on an NVIDIA Jetson Orin product. And we do various neural network functions. We do classification, we segment those images, we can do ranging on those images, and we can even fuse different sensing modalities using this software. And then we output this using something called a robotic operating system topic, or ROS topic, and that gives you that action. And if you were to then say, okay, well, what does that really look like, those things? This is what that software looks like visually. We can get from our software, we can just get a raw intensity image, intensity from thermal. That's what you see in the upper left-hand corner. We can also give you a object list or a bird's eye view in 3D space, so distance. So what you're seeing here in this video is these are objects that we've identified. We don't tell you what it is. That's not the goal of this particular output. It's just to say there's something there, okay? And we know what it is, but we're just outputting a 3D object list. We can also perform what I called you object classification and segmentation. I'll show you some videos that explain that in a minute. But basically, this is identifying this as a person and how far that person is away. And based on the distance, we change the color, okay, so that can be visualized. We also do what's called RGB thermal infusion. And you'll see right here, at night, we can see those little deer that are off to the left. But when we take a visible light camera and we combine it with thermal, we can get the color of that stop sign, which comes from the RGB camera, and we can get the best in visibility of the thermal imagery. And if I want to go really technical with you for a minute, what our OWL algorithm software modules do is, if you think of those modules, classification, segmentation, mono depth for ranging. In other words, we use one camera to give us this range. That's mono depth. If you just use each individual module, okay, that's how you get the object bounding box in 2D, or if you use this for ranging, you get the 3D point cloud. If you put them all together, again, very sort of technical in nature, we do what's called an object identification. So it's a person with a three-dimensional volume response. So we can take that pedestrian that we've identified and classified, and we can give it range and give you just that information about what's in that bounding box. And the reason that matters is there's lots and lots of data in the world, and you don't want to overwhelm your processor with extraneous information. So if you can just give it what it cares about, you don't have to take up cycles of the CPU, and you can make faster decisions with less power and a lower cost CPU. And that's what the goal is of these automakers, is how do you get just the information you need at the right time? So that's the software story.
Okay, so how does your thermal sensor is using monocular setup? Like it is like 3D monocular thermal imaging sensor, what I
Okay,
read.
yeah, I understand your question. I think you're asking is how does monocular vision work?
Yeah, yeah, yeah.
And right. So the simple way to just simply say it is we take an image that's coming in from our camera, and through very sophisticated neural network processing, we're able to determine a range of where that object is based on training and what's called ground truth. And it's a very difficult explanation to get into as to how monocular ranging works, but the simple way to say it is it's a proven technique. It's the way Tesla does a lot of their driving right now, or use cameras to determine depth. And it's a technique using neural networks to give you that depth. We have some papers that explain how that works, and we can get you some of those white papers to augment my answer. But it's a neural network processing technique to determine range.
Okay.
Okay.
So can you share some design challenges which you have faced while developing it?
Sure. I'm going to bring up a picture here that talks about how we build our product, our camera. And what you see here is Owl builds all of the devices that make up the camera. So it starts with what you see here, which is called a readout IC. That's a semiconductor device that has 1 million analog to digital converters, which basically takes the data from what's called a microbolometer, and that's what reads the temperature. And there's 1 million of these MEMS structures, microbolometer structures, that get read out by a corresponding readout IC, which is all these two chips are put together, and there's a lot of gates. It's a lot of complexity. It took a couple of years to design this chip, and then you build it at a semiconductor foundry, and this is put together, and these dies are put together in what's called a wafer scale package. So the complexity of putting 1 million analog to digital converters down, 1 million MEMS structures, and doing what's called wafer scale packaging, it gets all put together into a chip that's called a focal plane array. And that's what the final product, this is a graphical representation. I don't have a good picture right now to show you of what this device looks like. But to give you a feel for scale, that's what the size of the camera looks like, a little over the size of a US quarter. So this is a very small device. And you take this chip and you put it onto the chip by itself, you can't do anything with. So you have to have electronics on a board. And we put that on what's called a camera core. This is the way cameras are designed, but it's a very, because all the sophistication's in the chip, we make a very low cost camera core. Once this camera is on a PCB board, we then put it in a housing with a lens, and we output the signal to be read by a computer. And so the design challenges were the complexity of building these devices, packaging it in a small wafer scale form factor, and making it low power and corresponding low cost.
Okay. So how the sensor helps self-driving cars to avoid crashes and hurting people?
Sure. So I think a video of this is really going to help you understand this. So here, I'm going to run this video for you in a second, but this is a real life test of our camera and our neural network software. So this was done at a test track in Detroit, Michigan, in the United States a few months ago. And this is taking that new NHTSA, National Highway Transportation Safety Authority, mandate that is likely going to be produced here in the United States by our, or excuse me, released by in the United States here anytime now. And it creates a scenario. And that's that scenario with a oncoming headlight, which you see here in this image here, and a pedestrian walking across, and the vehicle has to safely stop. Okay, so we mounted our camera in this vehicle. We put a test driver in the car, and the test driver was instructed to not touch the brake, just control the car. And the goal of the test was to safely stop the vehicle such that it doesn't hit the test target or the test dummy, right? And it was doing that while there's oncoming headlights blinding the driver. And I want to show you what this looks like. So this camera is just here so people can understand what RGB cameras look like. This camera is the image that's coming out of the computer showing what happens. So the car starts down the road. You can start to see that we've identified the pedestrians on the side. We now see it's a pedestrian, and we stop 6.8 meters before we hit the pedestrian. And that is a very complex test because this was a child-size pedestrian. This was not a full adult, which means that there's less volume to see. It was a dark, cold, windy night. You'll even notice here and there in the imagery that there's a cable attached to this person. The reason the cable's there is not to pull them along. It's on a track. The cable is a power cord, which is used to make the dummy heated like a human, so it has a heat signature. You would have seen it anyway, but humans really pop in certain situations. And I want to show you what I mean by that. It's like a pedestrian is wearing a retroreflective vest when seen in thermal. So here is a video that we took in Las Vegas. So even if it's not dark, it's very bright. This is bright lights. The streets of Vegas are well known around the world for being super bright. So what this image does is it shows RGB on the left, and it shows what thermal sees on the right-hand side. So I'm just going to point out and think about your own driving experience. You know there might be something there, but you don't know really what it is, and your RGB image can't really tell you at all what it is. But in thermal, look how these images pop. You can see that there's, what, 4 pedestrians here, 5, 6 pedestrians walking across the street. And as we get a little closer, you can see exactly what's going on. But the regular RGB software has even missed this pedestrian because it's blinded by the light behind it. But we see it very, very, very clearly. And as you continue down the street here, I'm going to just stop here for a second. You can see in the thermal image, we've already identified this pedestrian, but you can't tell what's happening here. And I'm going to get really close up to it, and I'm going to tell you why it would have a struggle. This pedestrian has put himself in the perfect place not to be seen by a lidar system or a radar system or a visible light camera, but it can be very easily seen by thermal. Reason it can't be seen by radar is it would get spoofed. The radar, it's standing still, first of all. Radar doesn't do well with things that are standing still. It would be spoofed by this pole that it could think it's, yes, it's 2 things, but is it a short pole and a big pole? It doesn't know what it is. And LiDAR with reflecting lasers would reflect off of this retroreflective target, which is a screen of some sort at a bus stop displaying advertising. This person is also wearing dark clothes that is not very retroreflective. So we've identified this long before, and you can see we've already gone on to the next pedestrians and seen them behind. So this is how this works, and why pedestrians are or living objects are very, very easy to see and distinguish, because it has very high signal to noise ratio.
Okay.
So that's how this technology works.
Okay. So, what changes might happen in car safety because of this new technology being tested by car companies?
Right. So we hope to bring pedestrian fatalities down to 0. That's
Okay.
ultimately the goal. And by the way, we're not alone in this. If you look at the corporate objectives of Toyota, for example, they have a goal, and I don't 100% quote me on this, but it's, they, if you did I think it's called Vision Zero or something like that. It's a corporate initiative whereby I think 2030, they want to have their cars so safe that it will never hit a human. So that's ultimately what this is about. It's about pedestrian safety and saving lives at night. And that's what will happen if you have this type of technology. You can really see how it works. The question has always been the question you asked me a little while ago, which is a good question. What's different? It's about the cost, bringing it down so it can be cost effectively deployed into a vehicle, making sure people, the automotive manufacturers and the suppliers and consumers, frankly, are aware that there's a solution. And that's why stories like this, the ones that you're writing and the ones that are showing up in national worldwide publications like New York Times and Forbes are super important, because it's got to solve that problem of pedestrians dying. And that's what we're all about.
Okay, that's great. So, how vibration in the car affect thermal imaging sensors? Does they have any effect on it in,
None.
giving a clear image?
No, thermal imaging has been used by the military for years in some of the harshest environments of the world. The technology is really purely solid state and is not affected by shock and vibe.
Okay, so what process do you use for testing and validating the system's performance?
Yeah, I mean the best way to think of this is the automotive industry has many standards that you have to comply to in order to sell into the automotive world safely, and it's through the entire design cycle that you have to have your quality systems in place. So, for example, we at Owl just recently completed our ISO 9001 certification, which says that we have a quality organization for delivering completed products and a development methodology that is documented and consistent. The IATF also has standards, IATF 16949 and ISO 26262, and all these other standards, which are really applying to automotive grade. Okay, and there's standards within those. For instance, you'll see in this picture that I showed you here, it refers to this being ASIL B. And ASIL B is an automotive standard that talks about redundancy and how you guarantee redundancy and the qualification you have to do. So we go through all of those steps in order to release this product to be auto qualified.
Okay, so how do you handle software and firmware updates, especially considering the need for continuous improvement in AI system?
Yeah. So you're right. You have to always be able to give new updates. And frankly, you also have to retrain your networks constantly on incoming information. So we have to be able to do software updates in the field for our systems, and then our customers need to be able to give us their training data back to us. So we have automated systems which can push our software out to our proof of concept systems or our systems. And then we have a way for the data, if the customer, meaning the automobile OEM or the developer, not the consumer. This isn't something we're not talking to the consumer. Our customer is the automobile makers, which have their own privacy policies and bring all the data back themselves in an anonymous way. But as they give us new scenes that need to be trained, we would run this against our neural network training software based on the inputs that we get from their data. So it works both directions.
So, what are the biggest challenges you faced in scaling and deploying your solutions across different markets and different regions?
We're still at the earliest stages of our journey, so we haven't hit scale yet. This is still new technology deployments, so we haven't hit those expected scaling challenges. But through experience, we know how to build manufacturing environments that hit scale. We know how to build, we know what we have to do with the sales organization, marketing organization to hit scale. I'd say the biggest challenge that we've had is is really just continuing to scale the team technically, to bring in the best experts around the world, and to hit very aggressive development schedules in a timeline where foundry capacities are tight. In other words, our manufacturing capacities are tight. Tools are very expensive, and you have to manage your business very efficiently in order to make sure that you're spending your available capital in ways that are well, that are going to be most effective when you're trying to develop up your business. So being smart in your scalability. So hiring, cash flow, and working with your customers to achieve that.
So, are there any future enhancement or development plans for this, imaging sensor?
Sure. So we have roadmaps for both the hardware and the software to continue to change the resolution. There's different use cases for the size of the number of pixels you have. There's high definition resolutions. There's lower resolution. So we'll be continuing to augment our portfolio with different camera sizes, number of pixels. And of course, our software is something that we'll always be updating to improve the quality of the classification and the objects that we classify. Today, we classify, for instance, people, vehicles. We'll eventually make sure that animals will have different subsegments of animals. We'll have different poses that the pedestrians are in. So those are the type of things that you'll constantly be improving in the software as well.
Okay. So, how is real-time processing achieved, and what computational resources are required?
So I explained that a little bit earlier, and just keeping it at a very high level. Today we use an Orin NVIDIA processor, and that's designed specifically for neural network processing, and I don't really know how to answer the question beyond that. I'm not at liberty to go into the CPU cycles and some of the other technical details of how our processor architectures work, except just to simply say we use an Orin NVIDIA processor in today's use case.
Okay, so what do you think the future of car safety and navigation will look like, with this 3D imaging sensors?
Sure. So what we think will happen is you'll see cars that have sensors that fully surround the vehicle. We think that you'll see thermal cameras used in forward-facing vision. You'll see thermal cameras in rear-facing vision, and I'll give you a use case here in a second, and even in the side. So let me just talk to you about this one use case right here. This is a really impressive use case. There's a truck coming up behind you, and I don't know if you've seen them yet, but there are mirrors that are used based on cameras these days. It's not an actual mirror, it's a projected image in the place where your rear view mirror may go. So with thermal imaging, a regular camera would get washed out. You wouldn't be able to see the motorcycle that's coming up on the side view, because the bright lights are blinding you in the back. But with your owl vision on, you'd be able to very clearly be able to see with anti-glare, this blind spot reveal. Another use case with the side vision is in an urban environment. This is that scenario that I showed you the video. There's somebody walking across a pedestrian. There's an oncoming, so a pedestrian walking across, there's an oncoming vehicle. There might be a bicycle coming up from behind that you need to see, or there may be something from the side coming across and darting, so you need to see this scene. So we think that surround view, ultimately, of thermal images combined with RGB cameras, some radar, is going to make the cocoon of a car very, very safe, and safer for pedestrians because of that. That's the vision.
Okay. So, will adding this technology make cars more expensive for buyers?
No, that's the goal. You want to bring in new technology and keep the costs low. And that comes back to that cost problem I keep talking about. If I was trying to put a $10,000 thermal camera on every car, it would never get deployed. Nobody's going to buy that. Maybe a few high-end vehicles might, but that doesn't solve the problem. So it has to come down very, very low cost, and it will potentially start to replace some of the other cameras or radar or lidar systems that are used in a vehicle today. So you'll take out one type of sensing modality and put in a thermal sensor. Again, thermal won't be everywhere. You still need to see color, but it might reduce the cost. So if a vehicle has a $500 lidar system, by 2028, that $500 lidar system may be replaced by 2 thermal cameras at making it up $250. So the cost will be the same to the end consumer, but with a much safer technology sensor suite.
So, what do car companies think about your thermal imaging technology?
They love it.
Okay.
No, look, I'll give you as honest an answer as I possibly can. No automobile manufacturer wants to add cost or think about something if they don't have to, right? They just don't want to do it. There's something like 100 million cars produced a year. So they want to reduce their complexity. But a funny thing happens when governments mandate safety. They don't have a choice. So these mandates that are coming in from around the world are putting incredible pressure on a car company to do something. And this is not unusual. We've had safety in the United States. I can refer to this. I don't know in other parts of the country when these came in. But the reason airbags and seat belts are in a car is not because the auto manufacturers wanted to put them in. It's because governments mandated safety for the vehicle occupants. Consumers started to demand them. And eventually it got to the point where it could be widely deployed and easily deployed. Governments have ignored pedestrians for years. They've only focused on vehicle occupancy safety. Now that is changing. So these government mandates are going to force the automakers to have to deal with this. They're looking at all the different ways it can be done. So yeah, they're asking, can I do this with a visible light camera that I already have? The answer is no, they can't. And they are starting to figure this out based on those tests. They can't be done. Could I use radar? Well, maybe a little bit, but it doesn't solve another problem. What about lidar? Too expensive. So if they see a solution that will solve the government mandate problem, make their cars safer, they'll deploy it. So we're seeing a lot of interest from OEMs looking at this technology. And I think by production year 2028, you're going to start to see a lot of cars that use thermal images to save pedestrian lives at night. So thank you.
Yes, yes, sure. Thank you for your time.